Imagine for a second that you are strapped into a rocket.
Okay.
You are tearing through the Earth's atmosphere and you're going like Mach 5. The metal all around you is just groaning. The vibrations are violently shaking your teeth, and the pressure outside is, building exponentially with every fraction of a second you accelerate.
Right. Yeah, it's a terrifying environment.
Exactly. And there is going to be this exact, precise moment, like literally a fraction of a millisecond, where the physical stress on that vehicle hits its absolute peak.
Max Q.
Right. And if the structural integrity holds through that one single moment, you make it to orbit. But if it doesn't, the ship just tears itself to shreds.
It's basically the ultimate bottleneck of physics, right? And getting past it is entirely reliant on engineers knowing exactly when that peak stress is going to happen, long before the rocket ever even leaves the launch pad.
But how do they know? I mean, they can't just guess and check with $1 billion piece of hardware.
No, definitely not.
Figuring out the exact timing of that moment relies on a single, highly abstract mathematical trick. So welcome to today's deep dive. We are looking at a really fascinating stack of highly technical engineering notes today.
Yeah, specifically focusing on a concept called Day 14 Tower Function Derivatives and Applications.
Which I know. I realize that title probably sounds like the syllabus for some graduate-level math class that you actively tried to avoid in college.
It definitely sounds intimidating.
It really does. But here's the promise for you listening right now. You are not going to need a whiteboard for this.
Or a calculator.
Right.
Yeah.
You aren't going to need to memorize a single equation today. Our mission for this deep dive is to demystify this seemingly terrifying mathematical concept, this thing called logarithmic differentiation. We're going to explore how this one specific math hack, I guess you could call it, is the invisible scaffolding behind everything.
Oh, literally everything. From that rocket punching through the atmosphere to the artificial intelligence running on the phone right in your pocket.
Yeah. It really is the invisible architecture of our modern world. And to understand why this math trick is so crucial, we sort of have to start with the problem it was invented to solve.
Right, the conflict. So in calculus and, in physics generally, we constantly need to find the derivative of something. And a derivative is just a mathematical way of measuring a rate of change.
Like how fast is the speed changing or how fast is the pressure dropping?
Exactly. And for normal situations, there are standard tried and true rules for finding that rate of change. Let's say you have an equation with a constant base, like the number 2 raised to a moving variable exponent, 2 to the power of x.
Okay, great.
We have a standard exponential rule for that.
Because the base is anchored.
Exactly. The base is anchored. And it works the other way around, too. If your base is the moving variable, but your exponent is a constant number like x squared, you just use the basic power rule.
Right. Again, something is anchored. You have a constant somewhere.
But the material we are looking at today introduces this scenario where the math is fundamentally broken. It's called a tower function.
Yeah, and the quintessential example in the sources is the function y equals x to the power of x.
Yeah. And when you look at x to the power of x, the anchor's just completely gone. The base is changing, and the exponent is changing at the exact same time.
It's so slippery. Because if you try to use the old rules, standard math just utterly fails. You can't use the power rule because the exponent isn't a constant.
Right.
And you can't use the exponential rule because the base isn't a constant either. To me, when I was reading this, it feels like looking at this hopelessly tall tree that you need to measure, but you don't have a ladder. No. The exponent is way up there in the canopy, completely out of reach.
That's a really great way to visualize it. You basically need a way to bring that exponent down to the ground floor. And that is exactly what the logarithmic differentiation workflow actually does. It is this incredibly elegant workaround that starts with step 1, taking the natural logarithm, the ln, of both sides of the equation.
Okay, I want to pause here for a second. If I take the natural logarithm of the right side, the x to the power of x, how does that actually help me get the exponent out of the tree?
Well, it comes down to a unique mathematical property of logarithms. By definition, logarithms are essentially the inverse of exponents.
Okay.
So when you apply a natural logarithm to a term with an exponent, it mathematically unhooks the exponent and drops it down to the front of the term as a simple multiplier.
It's like a grappling hook.
Exactly. You throw the grappling hook up into the math, you catch the exponent, and you pull it down. So x to the power of x transforms. It literally becomes x multiplied by the natural logarithm at x. The tower has been leveled.
Everything is on the ground floor.
Right.
But wait, if I do that to the right side of the equation, the rules of algebra say I had to do it to the left side too, right?
You do.
So my nice clean y on the left side is now the natural logarithm of y. Haven't I just created a new mess for myself?
It definitely looks messier at first glance, but it actually opens the door to a technique called implicit differentiation.
Which is steps 2 and 3 in the workflow.
Exactly.
Yeah.
Normally, we like our equations neatly separated, right, with y all by itself on one side. But implicit differentiation lets us find the rate of change even when the variables are all tangled up together. You essentially take the derivative of both sides simultaneously. You apply the chain rule to the left side and the product rule to the right.
Let's try to avoid getting bogged down in the textbook definition of those rules.
Fair enough.
Conceptually, it seems like the chain rule is sort of like peeling apart a set of Russian nesting dolls just to see how the inner function affects the outer function.
That's a good analogy, yeah.
And the product rule just gives us a way to calculate the rate of change when two moving pieces are multiplying each other on that ground floor we just made.
That's spot on. And when you combine those techniques, you can finally isolate the derivative of y. You multiply the whole mess by the original function, and your unsolvable problem is actually solved. In the case of y equals x to the power of x, the derivative evaluates cleanly to x to the power of x times the quantity of the natural log of x plus 1. You successfully calculate the rate of change for a system where absolutely nothing is anchored.
Okay, so we have this really neat theoretical grappling hook to pull variables out of the sky.
Yeah.
And it works beautifully on a chalkboard.
Mm-hmm.
But let's take this out of the classroom for a minute and put it back into that rocket we were talking about at the very beginning. How does pulling an exponent down to the ground floor actually keep a spacecraft from exploding?
Well, it comes down to the environment the rocket is flying through. Planetary atmospheres, they do not thin out in a neat straight line as you go up.
Right.
They decay exponentially. And this is described mathematically by the barometric equation.
Okay, because gravity is pulling the air down, squishing it closest to the surface. So the drop in air pressure isn't steady. It curves downwards exponentially the higher you fly.
Precisely. Now think about the physics of the rocket launching through that specific air. We have a vehicle entering an exponential atmosphere at supersonic speeds.
Right.
Its altitude is changing rapidly, and its velocity is increasing rapidly. They are coupled, time-dependent functions. The engineers need to track the exact derivative of the structural drag, which comes from dynamic pressure.
And the notes say dynamic pressure is a combination of the air density hitting the rocket and the square of the rocket's velocity.
Right.
This is where it gets incredibly tense.
Yeah.
Because the air density is dropping exponentially, but the velocity is increasing quadratically. You have these two massive opposing forces basically crashing into each other.
And the intersection of those two changing forces creates this mountain peak of physical stress on the airframe. That is max Q, the point of maximum aerodynamic drag.
Let me put myself in the shoes of an aerospace engineer for a second here. If I didn't have this specific logarithmic derivative workflow, this exact rule, couldn't I just use a computer to run like discrete approximations? Like just check the pressure at 10,000 feet, then 11,000, then 12,000, and just kind of guess where the peak is?
I mean, you could try, but discrete approximations are incredibly dangerous when you're dealing with exponential curves at supersonic speeds.
Because it's moving so fast.
Right. Between 10,000 and 11,000 feet, the forces are changing continuously and non-linearly. A minor rounding error in an approximation could literally mean missing the true peak stress point by a massive margin. Logarithmic differentiation gives you the exact continuous rate of change of that structural drag. It pinpoints the exact millisecond of max Q.
Wow. So it takes the guesswork out of surviving the atmosphere entirely.
It has to.
And looking at this engineering material, the grappling hook isn't just used for the air outside the rocket, it's used for the mass inside the rocket too.
Oh, definitely. You're referring to the structural mass optimization for multi-stage rockets. They use something called the Tsiolkovsky rocket equation.
Right, which is fascinating because it highlights this brutal paradox of space travel.
The tyranny of the rocket equation.
Yes. If you want to go faster, you obviously need more fuel. But fuel is incredibly heavy. So to push the heavy fuel, you need
more fuel, exactly.
It's a compounding problem, which means, you guessed it, it's an exponential problem.
Yeah. The Tsiolkovsky equation actually relies on a natural logarithm to calculate the change in velocity based on the ratio of the rocket's initial mass when it's totally full of fuel to its final mass when all the fuel is burned up.
So to maximize what a rocket can actually carry to orbit, The payload engineers have to set up these massive sensitivity matrices. They're constantly adjusting the structural limits, shaving off a pound of metal here, adding a pound of fuel there. And to find the instantaneous rate of change in those complex payload matrices, they have to use logarithmic derivatives.
They use the grappling hook to pull those exponential mass constraints down to a manageable level so they can actually solve them.
Okay, so we've established that this math is absolutely essential for massive macro-scale engineering problems. We're talking about millions of pounds of thrust, extreme heat, atmospheric pressure.
Big stuff.
Really big stuff.
Yeah.
But what completely blew my mind as I was reading through these sources is that the exact same mathematical principles govern the absolute opposite end of the spectrum, too. The microscopic landscape inside the microchips that are controlling that very rocket.
It is a massive jump in scale, I know, but the physics are remarkably similar. We are moving from aerospace down into electrical and electronics engineering. So physically, we're talking about semiconductors.
The material highlights something called a PN junction diode. For anyone who is an electrical engineer, you can kind of think of a diode as a one-way valve for electricity.
Right, yeah.
It lets current flow in one direction, but physically blocks it from going backward. It is essentially the fundamental building block of literally all modern electronics.
And the way that microscopic valve opens is not linear. It is modeled by the Shockley diode equation, which is strictly exponential. As thermal energy and voltage interact across the microscopic barrier inside the diode, the current doesn't just, trickle through evenly. It scales up exponentially.
Like a floodgate bursting open.
Yeah. But engineers don't just want to know how much current is flowing at one specific second. They need to know how the current changes if the voltage wiggles even a tiny bit.
Because it's dynamic.
Exactly. That is called finding the small signal dynamic resistance. To evaluate how that microscopic floodgate reacts to tiny changes in pressure, the engineers have to evaluate the inverse of that exponential derivative. Again, standard math fails here.
They need the log trick.
They absolutely need the logarithmic workflow to evaluate the exact resistance dynamically.
And there's another application in the electronics section of the notes that I really want to unpack because it honestly feels like a superpower for a circuit designer. The material calls it fractional sensitivity analysis.
Oh, this is crucial for high-frequency analog circuits. Fractional sensitivity basically uses logarithmic differentiation to calculate a very specific ratio.
Let me see if I can translate the underlying concept here just to make sure I'm getting it.
Go for it.
Imagine a designer is building a complex radio transmitter for a satellite, right? There are thousands of microscopic resistors and capacitors. Instead of the engineer just asking a basic question like, how much does the total voltage drop? This math lets them ask a highly targeted diagnostic question.
Right.
It lets them ask, if this one specific microscopic component degrades by exactly 1% over the next 5 years, what exact percentage of my entire system's performance is going down the drain?
That is exactly what it does.
Yeah.
By taking the partial derivative of the natural logarithms of both the component and the system output, the formula mathematically filters out all the raw voltages and raw currents. It just leaves the engineer with a pure percentage ratio.
So it's basically a mathematical lie detector for finding the weakest link in a circuit.
Yes. It isolates the tolerance drift. It tells you that a 1% failure in component A might not matter at all, but a 1% failure in component B is going to cascade into a 10% failure for the whole board.
Wow.
It provides this insane diagnostic precision at the microscopic level, and it is all made possible by our logarithmic grappling hook.
It is incredible. The same exact math that stress tests the rocket's airframe is stress testing the microscopic hardware inside its navigation computer.
It's everywhere.
But according to the final section of our material, the most vital application of this math right now isn't happening in the physical hardware at all. It's actually happening in the virtual digital brains running on top of those circuits.
That's right. We're crossing over into computing and systems engineering now. Specifically, we're looking at machine learning, information theory, and algorithmic complexity.
Which I have to ask, how in the world does an AI use a tower function derivative? It doesn't have an airframe to break. It doesn't have physical valves to open.
It comes down to the fundamental mechanism of how an AI actually learns. When you train a multi-class AI, say, teaching it to recognize different types of road signs for a self-driving car, it makes predictions.
Uh-huh.
And a lot of the time, especially early on in the training, it's just wrong. The system needs a mathematical way to measure exactly how wrong it is.
And the material calls this the cross-entropy loss configuration.
Yes.
It's an error function. It calculates the difference between the actual truth and the AI's prediction.
Yeah.
And when I look at the underlying math of this loss function, it's heavily reliant on natural logarithms.
Yeah, and there is a very specific reason for that. AI networks use activation functions, specifically these things called softmax activations, to output their guesses.
Hmm.
A softmax function basically takes a bunch of raw numbers and forces them into a strict probability distribution that adds up to 100%.
Okay, I see.
And because of how it forces those numbers into a probability curve, the output is inherently exponential.
Oh, okay, I think I see the connection now. The AI is spitting out exponential probabilities, and the system uses a natural logarithm to evaluate how wrong those probabilities are. We are right back to step one of our tower function.
Exactly. We have an exponential and we use a log to deal with it. But just knowing it's wrong isn't enough for the AI, right? The AI needs to know how to fix itself. It needs to adjust the mathematical weights of its internal digital neurons. This process is called backpropagation.
Let's visualize backpropagation for a second.
Okay, sure.
Imagine the AI is like a hiker who has been dropped into a massive, pitch-black mountain valley. The bottom of the valley represents zero error-like, a perfect test score. The hiker obviously wants to get to the bottom, but they can't see anything. It's totally dark. All they can do is feel the slope of the ground beneath their feet.
And that slope is the mathematical gradient.
Right? If the ground slopes down to the left, the hiker takes a step to the left. The problem is, because the AI's outputs are exponential, the shape of this valley is incredibly steep and is constantly curving. So the logarithmic differentiation workflow basically acts as a high-powered flashlight.
I love that.
Right. It cuts through the exponential curves and calculates the exact steepness of the slope at the hiker's exact coordinates.
Yeah, without those exact logarithmic gradients, the backpropagation algorithm just couldn't find the slope. The AI would just wander around the dark valley forever, completely unable to actually learn or optimize its weights. Backpropagation literally is the grappling hook.
The AI is using the derivative of its own errors to teach itself. I mean, if an AI is the student taking a test, the cross-entropy loss function is the teacher's red pen.
Right.
And these logarithmic derivatives are the exact instructions the AI uses to figure out which digital neurons to correct so it gets a better grade next time.
Exactly. And, the material also touches on how this math applies to the scale of the computers running these AI models, too, something called algorithmic complexity.
Right, because all this data scaling takes resources.
It brings us to a major headache for systems engineers. When you model the hardware performance limits for a massive data cluster, you use big O notation. It essentially describes how the runtime of an algorithm slows down as you feed it more and more data.
And the sources note that the performance limits often hit a complexity bound expressed as O of n log n.
Right. It tells us that the delay in the system doesn't just grow in a straight line. Modeling that algorithmic delay requires evaluating its rate of change dynamically, which loops right back into these log derivative metrics. It is basically the mathematical warning light that tells an engineer exactly when their server farm is going to hit a wall and just crash under its own weight.
Wow. We have covered so much ground here, and the mechanics of all this are fascinating.
Yeah.
But I have a confession to make.
Uh-oh. What's that?
As much as I love understanding how the hiker finds the bottom of the valley or, how the exponent gets pulled out of the tree, I would absolutely hate having to actually do this math by hand every single day.
Oh, you are definitely not alone in that. And the good news is, modern engineers aren't just standing in front of chalkboards doing tedious tower differentiation by hand anymore.
Yeah, I noticed that at the very end of our material, the notes actually conclude with a standalone Python script. It utilizes a mathematical library called SIMPy.
Yes, SIMPy is a library for symbolic mathematics. It basically handles the structural mathematical execution automatically. You just feed it the function, and it applies the logarithmic differentiation workflow, runs the implicit differentiation, and spits out the exact gradient.
So we've reached a point where we understand the abstract scaffolding so perfectly, we've actually taught the computers how to execute the logarithmic derivatives for us.
Right.
We outsource the math to the machines so they can use the math to optimize themselves.
It is a completely closed feedback loop.
It's wild. Let's recap this deep dive because we went from the theoretical all the way to the virtual.
We really did.
We started with an abstract, seemingly unsolvable math problem. A tower function, where a variable is shifting in both the base and the exponent, leaving us without any anchor.
Standard calculus failed, so we used the grappling hook. We applied a natural logarithm to mathematically pull the exponent down to the ground floor, which allowed us to actually find its rate of change.
And from there, we saw how that one single mathematical trick ripples through the modern world. We saw how aerospace engineers use it to pinpoint max Q, the exact millisecond of maximum drag on a rocket tearing through an exponentially decaying atmosphere. We saw how circuit designers use it as a diagnostic lie detector, finding the fractional sensitivity and the exact weakest link in a microscopic silicon chip.
And finally, we saw how it acts as the flashlight in the dark for artificial intelligence, using logarithmic gradients to allow neural networks to navigate their errors and actually learn.
It really proves that this level of dense, high-level math isn't just, theory for the sake of theory.
No.
Or an academic torture device.
No, not at all.
It is deeply functional. It is the invisible scaffolding that is quite literally holding up every single piece of modern technology you interact with daily. The rockets, the electronics, the AI, none of it fundamentally works without this specific math.
Seeing those connections really changes how you view the physical world around you.
It really does. And I want to leave you with a final thought to sort of mull over on your own today. It builds on what we just learned about artificial intelligence.
Oh.
We know that the artificial neural networks we've built inside our servers rely entirely on these logarithmic gradients and exponential decay functions to learn and optimize their pathways. So think about this. Could the biological learning processes, the literal habit formations and memory encoding happening inside our own human brains, be governed by these exact same mathematical laws?
Oh, wow. That is a really profound question that makes you wonder if our own neurons are just biological tower functions, constantly evaluating our own derivatives to navigate the world.
It's entirely possible. So the next time you watch a rocket launch, or even just look at the phone in your hand, remember the scaffolding. Remember that behind the steel, the glass, and the code, there is a sprawling, invisible architecture of pure mathematics holding it all together. And sometimes all you need to understand it is a good grappling hook. Thanks for joining us. We will catch you on the next Deep Dive.